All right, welcome to video 2. This is going to be the last video that we go over the mesh current technique. In this video, we're going to be looking at the super mesh and other kind of strange things that can crop up while we're doing mesh current analysis. So first of all, let's do just one more mesh current example. And let's do a mesh current example now with a dependent supply. Now, in the previous videos, we did a couple of examples and we went all the way through the math. I'm not necessarily going to go all the way through the math with all of these, but I do want to kind of go through the process of these different styles of circuits. You'll get examples of these when you do homework, but it's good to just kind of see if something strange shows up. So this problem, we have 3 essential meshes that are pre-labeled for us here. And so we're just going to go around each one of these meshes and write these equations. So going around this first mesh, what do I have? I have negative 50 plus 5 times I1 minus I2 plus 20 times I1 minus I3 equals 0. And remember what we talked about, that when you're going around mesh 1, if you're doing clockwise loops, you should always see I1 minus, right? It should be consistent in that sense if you're doing clockwise loops. Students all the time ask, well, does it matter? Why did I have to? Can I do it in any orientation? You can do it in any orientation you want. But if you mix up your orientation of your loops, your math is going to be different. You're going to have to think about it each time. If you're consistent and just do clockwise, you get to pick. If you're consistent and do clockwise, you're going to start to see patterns show up. You're going to get familiar with the patterns, and it's going to minimize your chances of making a mistake. All right, let's go around the second mesh now, around here. So going around this, we're going to have 1 times I2. We're going to have 4 times I2 minus I3. Then we're going to have 5 times I2 minus I1. And that's just because going through the 5, we had I2 going this way, we had I1 going this way. So the current this way, in order to get the voltage drop in this direction, is I2 minus I1. Okay. And all of that equals 0. So now our last equation. I'm going to go through it like this. And we're going to say the voltage drop across this resistor coming from the bottom to the top now is going to be the current entering the bottom, which is I3. So it's going to be 20 times I3 minus I1. And again, we can think about that for a while, and we can think about which way it is. Or if we are consistent, we can just say, well, I'm analyzing my I3 mesh, so it's going to be I3 minus the other one, if we're doing clockwise loops. Okay. And then for the 4 ohm, we got 4 times I3 minus I2. And now, what's the voltage drop across here? Well, it's 15 I5, right? So one thing to note is this is a voltage drop, and it's just a voltage supply. It's a dependent supply, but it is a voltage supply. So we know the drop across here. It is 15 I5. And that equals 0. But what's the problem now? Now we follow the mesh current technique, and we have 3 equations, but we have 4 unknowns. Because the dependent supply gave us, we can treat it just like a voltage supply with this one little extra squirrely variable, but we do have to get rid of that variable there. So our question is now, we want to represent I phi in terms of I1, I2, and I3, because I1, I2, and I3 are the variables we have. They're the ones we're solving for. We got 3 variables, 3 equations. We can't have that 4th variable. So what is I phi? I phi is going to be labeled here as the current flowing down in this direction. We actually already have that expression hidden inside of our equations. We needed that current flowing down through the 20 ohm resistor when we were writing, the voltage drop across the 20 for the first mesh. So it is already there, or we can just think the current flowing down through this resistor, well, I1 flows down in that direction, I3 flows the opposite, so the current flowing down is going to be I1 minus I3. And I can just substitute that in here. Perfect. 3 equations, 3 unknowns, I'm done. This could have been anything too. Let's say this had been a voltage supply that was dependent on another voltage somewhere in my circuit. Well, then I would have had to represent that voltage using my currents I1, I2, and I3 times resistance. I would have had to find whatever resistance or supplies that voltage was across. I would just have to write the mathematical expression for that voltage in terms of my current variables. And then we're done. So really, don't overthink the difficulty with dependent supplies. Treat them like a normal supply as much as you can. And then sometimes you got to just write an expression for that thing that it's dependent on in terms of the variables that you're solving for. But once you've done that, it's fairly straightforward. And now we have an equation. 3 equations, 3 unknowns. Once again, just like in the example at the end of the last video, 3 equations is typically where I switch to linear algebra. So I'm not going to go through the process now in this example, but which does, I could be making a mistake here somewhere, and if I do, I apologize. I'll try to note it in the video if I did, but 3 equations, 3 unknowns, that's a math problem after this. Let's do another special case here. Let's do this. Do this circuit. So in this circuit, we already labeled once again IA, IB, and IC. So did I have A, B, and C? No, 1, 2, and 3 there. Yeah. All right. So let's just start writing this expression. So around mesh IA, we have negative 100 plus 3 times IA minus IB plus, what's this voltage drop across this current supply? I don't know. The problem with current supplies is what voltage is across a current supply? Whatever it has to be to maintain that current. What does it have to be to maintain that current? We don't know until we've solved all this. So we're in this situation where we don't know what this current is. We don't know what this voltage is. We won't know what this voltage is until we've solved for all of our unknowns in our circuit. So it creates an issue for us. So there's nothing we can do. We have no way to mathematically represent this voltage, so unfortunately we have to create a new variable. So we're going to say V is this voltage across this current supply. We don't know what it is. Now let's do IB. Going around IB, starting here, we're going to have 10 IB. Then we're going to have 2 times IB minus IC. Then we're going to have 3 times IB minus IA. And all that equals 0. Now let's go around IC. Going around IC, let's start here. Go around this loop. Uh-oh. Same thing. What's this voltage drop across the current supply? I don't know. But I do know that now that, because IC is swirling up in this direction through the 5 amp supply. But V was labeled negative side here, positive side here. So now I have to write this voltage drop as negative V. And now for the 2 ohm resistor, I have 2 times IC minus IB. And then I have 50. Okay. So unfortunately, we got this V. The good thing is, though, I got a positive V here and a negative V here, so I can add these equations together. So let's take this guy and add them together. So we got negative 100 plus 3 IA minus IB plus V plus negative V plus 2 IC minus IB plus 50 equals 0. Cool, I got rid of my V. But what's my issue now? Now my issue is I have one equation, two equations. I have two equations and still three unknowns. So just like in the case where we had a voltage supply between two nodes when we were doing the node voltage technique, the way we're going to get our third equation is we're going to say, hold on, that supply that was intersecting these two things is going to give us that other equation. In this case, yeah, we don't know the voltage here. We don't know this voltage right now, but we sure as heck know this current. This current is 5 amps. We have 5 amps flowing in this direction. But what is the current flowing in this direction? Well, the current flowing in this direction, what direction is that? That's IC flows in that direction, and IA flows in the opposite direction. So the current, the 5 amps flowing in that direction is going to be IC minus IA. Boom, third equation. Now we're off to the races. 3 equations, 3 unknowns. So just like in the case of node voltage, in node voltage, when we encountered this situation, we gave it a special name, and we had a special way of saving ourselves the effort of having to combine 2 equations to get rid of a variable. And we called it supernode. Well, now we're going to do the same thing here. We're going to call it supermesh. But once again, I want to stress that calling this its own special technique and doing the technique its own special way, it doesn't save us that much effort over just writing the 2 equations and canceling out the variable. So just keep that in mind, that it is a technique. We do give it a very impressive name like supermesh, which is, but it's not saving us that much time over just this approach where we create a variable and substitute it. But it's still worth it. Okay. So what is supermesh? Supermesh is basically where we say, let's pretend this doesn't exist. Let's pretend this doesn't exist, and let's just pretend we have this one giant mesh in here. And let's write the equation for that mesh all at once. All right, let's do that. But the one thing we got to be careful about is, even as we're writing this equation all at once, this current is still IA and this current is still IC. We still have 2 different current variables. So as we're moving around this super mesh, we still have to be careful about, am I in the IA loop or am I in the IC loop? Okay, let's do it. So we have negative 100 plus 3 IA minus IB plus, now we're writing the voltage drop here. That's going to be 2 times IC minus IB. Now we got 50 volt drop. Now we got 4 times IC. Oh, did I forget about that before? Look at that. 4 IC. Sorry, you're probably yelling at me. I did catch it eventually. Okay. 50 plus 4 IC plus, lastly, we got the 6 ohm, but the 6 ohm was IA plus 6 IA equals 0. So, looking back, that is I forget. Oh, I forgot the 6 here. Oh my gosh. I gotta go back and redo this. Nope. Not gonna go back and redo it. I'm gonna own the mistake. I'm not gonna go back and redo it. I'm just gonna go. Yep. Okay. That's 2. I forgot. That's the thing. That's why these bottom rows, that's why we like them to be a nice clean wire that we call 0 volts. Everybody likes a nice clean wire on the bottom of our circuit. We forget about that bottom row there. All righty. So super mesh is we write this whole loop all at once. So we're just going to write it all at once, but the equation ultimately is the same. So ultimately the equation is the same as this one. Once we added in our once we added in the pieces that we forgot, the equation is exactly the same. Okay. But let's do IB now. So we did the super mesh. Now let's do IB. So we're going to have 10 IB plus 2 IB minus IC plus 3 IB minus IA equals 0. Now, whenever we use super mesh, we do have to add that extra equation. That extra equation is always going to relate the two currents that are intersecting where that current supply is with the value of the current supply. So in this case, again, we're going to have 5 amps, 5 equals IC minus IA. And again, why did I know that it was IC minus IA? Because 5 amps, the current supply was facing this direction. That's the same direction that IC flows, and it's the opposite direction that IA flows. Positive IC, negative IA. Okay, so after disastrously flubbing that example on the previous version, maybe the super mesh did help. Maybe the super mesh actually got me to finish writing my mesh equation by going all the way around that super mesh. Anyway, so that's the approach. That's the super mesh equation. That's how we can directly write this expression. So now we have 3 equations, 3 unknowns. We can solve for these. Okay, that's super mesh. Special cases. Just to quickly talk about some of these other things that show up when you're doing, or some of these are things we've already talked about. What happens when you have something like this in a mesh current analysis? Well, the cool thing is, if we were writing the mesh currents here, I1 in this case is already known. What is I1 in this case? It's -2. So whenever we have a mesh and there is a current supply that is the only current flowing through that current supply is the mesh current, then the mesh current is known. So when this happens, when you're doing a mesh current analysis around a mesh and you encounter a current supply, one thing to stop and say is, if the only current flowing through this current supply is the mesh I'm solving for, or I'm writing the equation for, then it's known. My mesh is known and I'm done. I don't need to write this KVL equation. I know this mesh current in this case is -2. What about this case, where you have a current between 2 meshes? Well, this is the case that we just went over. This is where you need super mesh. And what about where we have a voltage supply here? Well, voltage supplies are easy. Voltage supplies with mesh current are just like current supplies with node voltage. Remember, with mesh current, we are writing the Kirchhoff's voltage law equation. So we're writing a bunch of voltage drops. So if we're given a voltage supply, game on. Right? If we're given a voltage supply, okay, I know what the voltage drop is. I can immediately look at it. I got 20 volts dropped across this thing. It's a 20-volt supply. It's easy. Challenge is, after we've done mesh current, what if we need to know the current flowing through this voltage supply, right? So finding, oops, oh, sorry, not yet. What if we want to find the current through this voltage supply? Current through this voltage supply is just going to be the combination of these 2 meshes. So after we solve for the meshes, we can just combine them and find the current through the voltage supply. That will allow us to do things like find the power delivered by, dissipated by, supplied by, whatever term you want to use for power. That'll let us find the power for the voltage supply. What about with the current supply? What if you were analyzing this and I said, what is the power supplied by this 6 amp supply? Even after you solve this circuit using super mesh, how do you find the power for a current supply in a in a mesh current analysis? Unfortunately, the only way to find the voltage across this current supply is to do the KVL equation around the loop. So unfortunately, there's no shortcut. We have to kind of, if we were going back to this expression, we would essentially be going back to this equation over here and then solving for V using our unknowns. But another way to think about it as, if let's say I'm trying to find, let's say I'm trying to find the power for this current supply. I want to find the voltage oriented like this. I want to find the voltage oriented like this because that's going to allow me to use the version of the equation power is equal to I times V, right? Because I have the labeled current entering the positive terminal. So how do I find this voltage oriented like this? My way of doing it is typically I will start here. I will start at the positive terminal and add the voltage drops up as I go from the positive terminal to the negative terminal. And whenever the sum of those voltage drops is, that's my voltage. So I would have, in this case, this voltage is easy to find. This voltage is easy to find if we know the current. This voltage is obviously easy to find. I would have just added up those voltage drops to give me the current to find the power. So this you might come back to this page a few times as kind of the how do you handle these special situations. These are just some quick things I wanted to talk about before you go in and start doing the homework problems. Some of the homework problems will have you deal with these kinds of situations that are presented on this page. And a lot of these, again, these are the complement of the same sorts of issues we dealt with node voltage. So with node voltage, the tough thing to find is finding the current through a voltage supply in node voltage. There's no way to do it other than just doing the Kirchhoff's current law at that node to find whatever current's remaining is the current flowing through that supply. So it's a similar thing here. Okay, so that is the end of our discussions about the mesh current technique. Practice, 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 do lots of practice problems. When we resume in the next set of videos, we're going to talk about some other approaches we can use for solving circuits, mostly approaches we can use as kind of a shortcut or approaches that are useful if we're only trying to find a limited thing about a circuit. So we're going to talk about, one of the techniques we're going to talk about is called superposition. And that's mostly useful for if we're just trying to find one unknown in a circuit. And the other technique we're going to talk about is combining supplies. We're going to find the equivalent supplies, equivalent systems for our circuits by doing supply and resistor combinations. So some fun little sort of grab bag things at the end of chapter 4. Chapter 4 is a big chapter. We spend a lot of time on it, but it's an important one. And we don't try to do chapter 4 in 1 week. We let chapter 4 be 2 or 3 weeks for a reason. It's a big chapter. It's got really important stuff. I will see you next time.